My name is Kathy Hill, and I am Principal Manager Carbon Storage at the Global CCS Institute. Today's webinar is on the long-term fate of CO2 in the subsurface environment, and we are very pleased to have two presenters from the British Geological Survey with us today. Mike Stephenson is Head of Science in the Energy area at the BGS. His education has included a BSc, MSc and PhD from the University of Sheffield and Imperial College London, as well as various postgraduate teaching qualifications. He began his career as a school teacher in rural Africa and stayed there for almost 10 years, but returned to pursue research. He has published over 65 scientific papers, as well as working extensively as a consultant for oil companies and working widely in the Middle East, including the Oman and Saudi Arabia, Asia, including Afghanistan, Pakistan and India, Africa and the Far East. Mike now runs the energy program at BGS, including carbon capture and storage, hydrocarbons, renewable and unconventional energy. He sits on the boards of several journals and is editor-in-chief of an Elsevier geological journal, Paleobotany and Palynology. So his expertise runs far and wide. Mike has a special professorship at the University of Nottingham and an honorary professorship at the University of Leicester, and is the first director of the Nottingham Centre for Carbon Capture and Storage, which is a joint venture between the BGS and the University of Nottingham. Our second speaker, Jonathan Pearce, has more than 24 years' experience with the BGS. He's been involved in CO2 storage research since the early 1990s and has led a number of research projects on long-term geochemical processes and the development of shallow monitoring tools in CO2 storage. More recently, he has developed expertise in CO2 storage regulation and strategic development, as well as undertaking due diligence reviews for a number of research, pilot, and large-scale demonstration projects internationally. His research has allowed him to collaborate with other researchers globally, including in China, Australia, Canada, South Africa, and widely across Europe. He has been involved in a number of research networks and conference organizing committees, so we're very pleased to have such widely experienced and internationally exposed researchers with us today. As far as questions, they're most welcome during the course of the webinar, so please submit them when you please through the GoToWebinar control panel that you can see on your screen. We will chat with you through the control panel to determine if you would like us to pose the question on your behalf, or if you would like us to unmute your microphone and pose the question yourself. Please give us your name and affiliation at the time that you pose your question. If we can't get through all of the questions today, and that's a distinct possibility given the number of people that have logged on, then we will endeavor to set up a second time with Mike and Jonathan in the next few days when you can pose your questions and provide a recording of the answers. This webinar will be recorded and is available on our website, or will be available on our website, along with the slides used in the next few days. And the Institute will email you when it is available to download, based on your subscription to the webinar. So without further delay, I would now like to hand over to Mike to commence the presentation.
Thank you very much, Kathy. I assume that people can hear me. So Jonathan and I are going to give you about 25 minutes on the long-term fate of CO2 in the subsurface environment. And that rather odd image you can see in the top left of the slide will become abundantly clear, we hope, in the next 20 minutes or so. So, first of all, I hope you can see me moving through these slides. You might ask why something as esoteric as long-term fate of carbon dioxide, in other words, what happens to CO2 in the rocks in the long term, why that would be relevant or interesting to anybody. But in truth, it's really a very relevant thing. It's relevant to regulation because governments that need to regulate the storage of CO2 need to know what happens to CO2 in the long term in the rocks, so they can develop appropriate rules. But also, public investment, public confidence is important. So, in other words, if the public are reassured that something is okay, that CO2 isn't going to do anything we can't predict or don't want to happen, if the public is reassured about that, then we'll have public confidence. And the public is sensitive to long-term. Investment as well is important, because if you can't convince investors that we understand the processes that are going on in the long term, then no one's going to invest in this technical fix for climate change. So that's why it's relevant. And I'll just hand over to Jonathan now, just to give you an idea of the EC directive.
So good morning, everybody. So this is just a quick view of the directive here. Just one slide. One of the most important aspects of the directive, the principal objective of the requirement for CCS in Europe, is the permanent containment of CO2. And this is quite a challenging objective to demonstrate, perhaps not to actually technically achieve, but one of the issues that people are grappling with now is how you actually are able to generate enough evidence to demonstrate that you will be able to store CO2 on a permanent basis. So one of the key issues of being able to address this is by looking at the static model, by developing a very good understanding of the geology at depth around your storage site, so that you can demonstrate you have a good understanding initially of how your CO2 might behave. And as we go through the presentation today, we'll be able to come across some of the processes that control that. One of the very, very important motivations for being able to demonstrate that you understand how CO2 behaves over the long term is this very long time scale of likely CO2 storage projects. Some CO2 storage projects may last over 50 years. This creates one or two challenges, particularly for industrial developers, because they want a very, very clear understanding that if they undertake an appropriately monitored and well-managed CO2 storage operation, at the end of that period they are not going to be left with any liability for the storage site, and therefore they can hand that storage site and hand the liability back to the member state, back to the government or the national authority, because this is very important for them to be able to undertake their initial investments.
So what I'm going to do now, having tried to establish the importance of long-term faith, this is not an esoteric or something which is far beyond our need to worry about. It's something we do need to think about. Before we go on to our understandings of long-term fate of CO2, what I'm going to do is go through the basics of storage. And forgive me if you are a geologist with lots of experience in storage, but I think for people who are logging on who are policy people or government people, some few slides on the basics of storage are appropriate. So first of all, this is a photograph of sandstone. It's the Bunter sandstone in a quarry in eastern England near Scunthorpe, and it's a red sandstone. If you look at it in using a microscope, what you see is the grains here and the spaces in between the grains, and the pore throats between those spaces. So for example, you can see one here. And this is the Bunter sandstone, which will almost certainly be a target for storage in the UK in the next few years. And essentially, storing carbon dioxide means putting the CO2 in the spaces between these particles. It's really as simple as that. But the problem is, if there is a problem, that these spaces are not empty. The spaces are full of fluids, usually saline water, sometimes fresh water, if you're lucky, oil or gas. And essentially, what you do in CCS is push that water out of the way. You shove the water out of the way and you replace it with CO2. And this slide shows the process of moving the water out of the way and replacing it with CO2. So essentially, that's the basic part of carbon CO2 storage. But the important thing to remember about storage is that time matters. because CO2 is a reactive gas, it does things in the reservoir over time. And we have time over here on the left. When we first of all put CO2 into the rocks, it will be in the form of a free CO2, not dissolved supercritical CO2. And we normally associate this kind of free CO2 with physical trapping. So in other words, trapping rather like we trap oil and gas. But later on, the CO2 will dissolve in water, in the brine, and we essentially have a solubility trap whereby CO2 is dissolved in water in the brine becomes slightly denser than it would have been before, and it begins to sink. And thirdly, after a much longer period of time, we have possibly carbonate minerals forming, so CO2 or dissolved CO2 in brine reacting with the minerals in the rock in which they're stored and turning into carbonate minerals. And one of the things that we're interested in here at the British Geological Survey and the Nottingham Centre for Carbon Capture and Storage is the time at which these happen. When does free CO2 mostly turn into dissolved CO2? When does dissolved CO2 mostly turn into carbonate minerals? And of course, carbonate minerals, and here we have some carbonate minerals amongst grains of sand. This is the holy grail of CCS because you're putting away the CO2 permanently in a rock which should never ever leak, or it's impossible to leak. So much of our research is revolving around how long and what are the processes which these CO2 with which CO2 turns into either dissolved CO2 or carbonate minerals. So time is important in this area. Let's have a look at physical trapping first of all. And this is a very big anticline here in, I think, the Rocky Mountains. A lot of geologists will fall off their chairs if we suggest that we're putting CO2 in an open structure like this, but this is just to show you, if we were to drill a borehole down into this anticline here, and if we were to have a great big seal of impermeable rock above it, and if we were to put CO2 into that, to push it, inject it in, what you'd essentially be doing is pushing the water away from those between the sand grains and storing it in that rock structure. And that's the simple process behind physical trapping, because the CO2 will sit underneath this seal. And in oil and gas, this has been shown to have been a successful trap for millions upon millions of years. We know that oil and gas has been kept in traps like this for 40, 50, 60 million years. And this is one of the reasons why geologists are pretty confident about physical trapping even before you get to solubility or carbonate trapping. But there are some things you need to know about physical trapping. And one is the idea that you have closed and open systems. And what we have here is a very nice road cut. Here's a truck for scale. You have this beautiful pink sandstone here, which you could regard as a tank for storing CO2 in. And let's imagine we drill a hole down into that, a borehole, and we have a fault here. You can see the fault and the fault here. Let's also imagine we have a seal here and perhaps an impermeable layer here. So essentially what you've got in this sandstone tank is a confined tank which can't easily move anywhere. So if we were to inject CO2 and push the water out of the way, the problem would be is that the water has nowhere to go. And if you were to inject too much and to put too much pressure in, you could get the pressure in the tank reaching the pressure that is exerted by the weight of the rock above. And that would cause cracking and a failure of the reservoir. So we have to understand when we're dealing with when we're dealing with physical trapping, whether it's an open or closed system. So at the British Geological Survey, we've been doing physical trapping simulations on the Bunter sandstone. The Bunter sandstone is that sandstone you saw in the second slide, the red sandstone. This is what it looks like in this area here, offshore the United Kingdom in the southern North Sea. It's very thin. You can see how thin the layer is. It's got a lot of topography on it. It's a bit like a blanket that's been rocked up on a surface. Here is where the Bunter sandstone is quite shallow. It comes close to the seabed here. Here is where the Bunter sandstone is deep, a couple of kilometers deep. And we did a simulation over an area about this size. This is the area here, and this is the area in red. And what we did, this is again in terms of physical trapping, is we simulated the injection of 3 power stations per year, that's about 30 million tons per year, for 50 years in 12 injection points. And you can see the injection points here. This is the contours, these are the contours on the Bunter sandstone in the previous slide. You see the size of our simulation is quite large. This is the saturation, so it shows how much CO2 is, how much of the pore space is filled by CO2. So we've got quite high percentages here. But what this essentially shows is after 50 years, we haven't filled very much space. We've been able to take 3 power stations per year for 50 years, and we haven't filled up that much of the space. But that's not the whole story. As I showed you before with the closed and open system idea, we really should be looking not just at the saturation of CO2 in the reservoir. We should also be looking at the pressure in that same reservoir. Now this is the same area with the same outline, but now we're showing pressure, not CO2. So this is the pressure of the formation fluid. And here are the 12 injection points that I've just shown you. And what's interesting here, we have an open system. So here we're assuming that there are no faults or structures sideways which confine the movement of water. So pressure can be alleviated more easily. But what you can see is the colors are mostly green. Now, this is slightly subtle here, percentage of lithostatic pressure. Rather than showing simple pressure, we've shown the percentage of lithostatic pressure, so the percentage of the weight of rocks above. And you can see generally the pressures are very low and very manageable. In 2 places we have rather high pressures, and that's because they are very shallow, so lithostatic pressure is rather low, so we actually get quite close to lithostatic pressure quite early. So we'd have to be a bit careful here because we could fracture the reservoir, we could have some brine moving from the reservoir into the sea here. But that's after in an open system. If we now look at a closed system, again we're looking at exactly the same area, and we imagine we have a few faults which are confining the movement of formation water. And you can see that overall the pressure is a bit higher, and we have reached rather high percentages of lithostatic pressure in several locations, again because they're rather shallow. So it's very important to manage pressure in these things. It's very important to understand whether you have a closed or an open system. And this is another area, and we're still dealing here with physical trapping. Later on, Jonathan will move on to solubility trapping. But this is some more modeling and some more simulation we've done, again for the Bunter sandstone. And what we have here is a bit of the Bunter sandstone. Again, it's a very thin layer. And what we're imagining now is we are injecting for a bit longer. So here time is telescoping out to 1780 years now. And again, we're going to look at the amount of CO2 in the reservoir. So this is after 0.1 in a year. We just see a blue dot appears. That's the start of CO2 injection. That's after 1 year. After 2 years, I hope we haven't got a lag on this, but after 2 years you can see CO2 appearing there. After 3 years, after 5 years, after 7, and you can see essentially that this area of CO2 in the injected part of the reservoir is expanding radially, mainly because the pressures are being applied radially by injection. That's 10 years, 15 years, 20 years, 24 years, 30 years, and again you can see this wider. What you're beginning to see now is the buoyancy of that free CO2, non-dissolved CO2, starting to exploit these higher levels within the reservoir. That's 40 years. Now, if we stop injection at 50 years, what happens? Well, injection is stopping at 50 years. There's no longer any injection. What happens is the radial effect of the injection decreases after 75 years, after 100, and we're beginning to see the CO2 essentially moving as a free, non-dissolved substance moving up underneath the track, trying to find the highest point. And if you've correctly located your store, it should be no problem because it's just looking for the highest point. That's 900 years. You may get residual trapping along the way, which is a bonus. at 1,000 years, at 1,500 years, and I think we finally finish on 1,780 years. So we feel through modelling and simulation we have a pretty good understanding of how free CO2 moves. What I'm going to do now is hand over to Jonathan to see a little bit about solubility trapping.
Yeah, thanks, Mike. So here we have some simulations here, looking actually at a simplified version of a real reservoir. This is the Utsira formation at the Sleipner CO2 storage project, which is a 1.2 million tonne per year CO2 injection from natural gas. This is CO2 as part of the natural gas stream that's separated and re-injected into a shallow saline aquifer called the Utsira formation. This is a couple of simulations I'm just going to run through from our colleagues, Eric Lindeberg at SINTEF, which is a Norwegian research institute. So as Mike's just been explaining, CO2 initially, as it was injected into the reservoir, remains as a free gas. And on the left-hand side of your screen, you can see the concentration of CO2 in a gas phase as a plume. Injection point is at the base of the reservoir, which is down here. And this is injected, as Mike just explained from the previous slide, the CO2 will rise under buoyancy because it's less dense than the formation fluid to the top of the reservoir, which occurs at the top of the simulation just here. And here we have a first screen view of 2.3 million tonnes of CO2. As we continue to inject, the CO2 chimney, if you like, with the CO2 plume increases and it starts to spread out under this cap rock here, the northern shale, under buoyancy as it reaches the surface. As it's migrating up through the reservoir itself, because it's a reactive gas, part of it starts to dissolve in the formation fluid that it's coming into contact with as it migrates through the pore space. After 20 million tonnes of injection, we can see now that the free CO2 gas is migrated, is spreading laterally out along underneath the impermeable cap rock, and also has started to spread out under some intraformational seals, some thinner, much thinner, partially complete mudstone layers within here, and it's starting to spread out laterally along those as well. And we can also see the amount of CO2 that is dissolved into solution has also increased. After another 50 years or so, CO2 injection has now stopped for 50 years. Most of the free CO2 gas has moved, has migrated up to the top of the reservoir and has spread out there. There's some residual free gas trapped under these intraformational mudstones here. But what's also beginning to happen now is that more and more of that CO2 is starting to dissolve. And as we go forward in time to 2,270 years, so another, let's say, 200 years in the future, we can see that the proportion of CO2 that's dissolved into the formation has increased. And as the CO2 dissolves, it actually increases the density of that formation fluid. So the CO2 saturated formation fluid, the CO2 saturated saline water, is more dense than the surrounding water, which is here just essentially black. And as it does that, under gravity, it starts to sink, essentially. So this is therefore increasing the safety of the storage solution, because what it's doing is it's taking the saturated formation fluid away from that cap rock and putting it further down towards the base of the reservoir. We can actually simulate this in the laboratory. Here we have two panes of glass. You're looking perpendicular through two panes of glass here, about 50 centimetres by 50 centimetres on each dimension. The grey area is filled with a saline fluid in which has been dissolved a pH indicator. At the top we have some free CO2. Now this is not at any reservoir conditions, this is purely at atmospheric conditions. But what happens is that over time, if we just look down here, we're now 60 seconds into this simulation. There's no sand in here, there's no porosity, it's just a completely open cell. With time, the CO2 begins to dissolve into the saline fluid. As it dissolves, it lowers the pH slightly, and we can detect this through a colour change in this fluid. It goes to yellow. After about 105 seconds, we can begin now to see that some small, density-driven plumes on a very small scale are starting to form. And as with time now, 195 seconds, just over 3 minutes, these are starting to form, and they start to sink, and will sink right to the base of this cell and cause slight circulations in the cell as well. So we can see this process in the laboratory, and we can simulate it quite successfully. So we know that many of these processes occur over quite long time scales, over geological time scales. CO2 solution in the formation fluid will start to occur almost as soon as it contacts the formation fluid, but most of that CO2 will not dissolve until well after the end of injection. One of the key questions, therefore, is what is the long term? How far do we have to predict the behaviour of the storage site? How far do we have to extend our simulations of these processes? This graph is a fairly famous graph that's been shown many times now, and what it tries to do is get over the concept of these different trapping mechanisms. So far, we've talked about the physical trapping that Mike explained. We haven't talked in a lot of detail about residual CO2 trapping, but that can be quite an important process. And over increasing time, shown here on the bottom axis, solubility trapping, i.e. dissolution into the formation fluid, and eventually, possibly, in some reservoirs, some mineral trapping. These start to occur over very long timescales here, 1,000, 10,000 years, geological timescales. So what we need to be able to do is try and understand how we might define some of these long-term processes. And here we've got some suggestions here. For example, do we have to simulate and predict the behaviour of the reservoir, behaviour of that CO2 plume until all the CO2 is dissolved? Probably not, I would suggest. Do we have to simulate the processes until CO2 migration has essentially stopped, so the physical amount of physical movement under buoyancy has stopped? Maybe that might be a suitable definition, suitable criteria in some systems, or even where some more chemical, physico-chemical stability has been reached. So hopefully you've now understood the concept that there are many different geological, geochemical, geophysical processes that occur within a reservoir to help retain the CO2 over the long term. One of the important things, therefore, is being able to demonstrate that at the end of a CO2 storage project, you can show that the system is going to be safe going forward in time over thousands of years. This is fundamentally based on your static model, your understanding of your site, your understanding of the geology, and we've seen some examples here from the Blunter sandstone, at least at a regional scale earlier on. Then the predictions, some of which we've given you a couple of examples of this morning, need to match with the monitoring data that you can acquire during your injection process. We haven't really talked about monitoring a lot this morning, but essentially you can track the plume movement in real time during your injection process. And what you're hoping is that that real data matches your predictions, your model predictions. And so at the end of your injection period, what you might want to be able to say is that your predictions are robust. They match your real data within a certain percentage, for example, for given parameters, that you haven't been required to revise your static model too much over perhaps, say, 5 years or so. These are suggestions that have been put forward in Europe under the European regulations, but I think have probably more generic validity elsewhere as well. This raises a few questions about what is an adequate match. Is it within 5 or 10% or more? We don't know at the moment. That's not really been tested in any regulations. And it's likely that these ranges are going to vary by parameters and by specific storage sites and storage conditions. There may even be more than one unique solution as well. So these are issues that need to be addressed. And it is fundamentally accepted that your initial models prior to injection will almost certainly need to be revised if you require more monitoring data. So essentially what we're saying here, that these models are used to predict future performance, and these will be based on site characterization. They will be revised during monitoring as well, and it's likely that the regulators will want to see how those models have been revised during the injection process. So just trying to summarise all that I've just been through and all parts that both Mike and I have been through, essentially as CO2 injection starts, the CO2 plume will tend to migrate upwards due to buoyancy because it's less dense. As it dissolves then, it will start to sink, so things start to go down, and over much longer periods of time, given the right reservoir conditions, some of that CO2 will start to precipitate out as mineral form, as a carbonate mineral. So we can visualize this on a profile of let's say risk, where during the injection period we might have relatively high risk because the CO2 is under buoyancy, is trying to reach up to the surface, to the land surface or the seabed surface. At the end of injection, that pressure, as we've seen from the simulations in the bunter, stops. It then starts to continue to migrate, and then with dissolution it will start to decrease, and going forward in time, that will start to reduce the risk profile. At some point, we're not quite sure where, dissolution will start to take over, and indeed mineralization will also start to take over. So really what we're trying to say is that these model scenarios will need to be conservative, and that we have to take conservative values for many parameters to show that we're going to be safe with our CO2 storage. We have to define acceptable ranges from these stable values that we can expect within our reservoirs during the monitoring period, during the injection period. These models need to be able to predict the stability of the plume, obviously with no evidence of any future leakage. And it's quite likely that some of these parameters that will be used to demonstrate safety at the end of a storage project will have to be defined quite early on. And I think that's perhaps one of the challenges that operators and regulators will have to address in the near future as we move to a more regulated storage system. So to summarise then, I'm going to hand back to Mike now, and he can sort of try and conclude.
Thank you very much, Jonathan. So we've been through quite a lot there. It's not, and we are, I think, probably slightly running over time, but essentially the conclusions are that the key trapping mechanisms, which we've discussed in some detail here, are physical containment and CO2 dissolution. We haven't talked much about residual trapping, but we didn't really have time. Mineral trapping, we'd like to know more about. It's something that probably needs quite a lot of research. What we should say is that most oil and gas geologists, most CCS geologists think that physical containment is enough because oil and gas has been kept so well in structures like traps. But it's always helpful to demonstrate these other things which increase security. And as said, Jonathan so clearly shown, demonstrating long-term performance is fundamental to transferring long-term liability to the state. And of course that is what controls how likely big investors are to invest in this, this idea. And that's perhaps the largest and most important point that we can make is that all the science so far is suggesting that storage risk goes down with time. So that's the end of our presentation. I hope you enjoyed that. But just some acknowledgements for some of our staff at both at BGS and NCCCS. And now I'll hand over to Kathy on questions.
Well, thanks very much to you both, Michael and Jonathan, particularly for that informative presentation. Nice, clean, and clear graphics, especially useful to have the animations there to just see how the process is modeled. We've had a number of questions come in, and I'll just start off and kick off with them. We've had a question from Nick Hoffman, who's based in Melbourne with the Carbonet project in Victoria, Australia. He's got a fairly specific question about the open systems pressure set of slides. And it refers to the Bunter or the Bunterstein sandstone, and it says your open system pressure seemed very high in that case study. Surely the Bunterstein, I'll say the Bunter, has had a better aquifer than, has a better aquifer than this. Would you care to comment on that, Mike or Jonathan?
So yeah. I mean, I was not involved in the original simulation, so I can't comment particularly on the pressures chosen. But the Bunter is certainly one of the primary UK targets for CO2 storage, and indeed for storage in southern North Sea generally, and certainly if CO2 storage takes off onshore, as well in other parts of Europe, then it will certainly be a primary choice for CO2 storage. What we're trying to simulate here is the local, if you like, increase and regional increase in pressure around these injection points, up to 80% of lithostatic pressure. So unfortunately, I don't have the original starting pressures that were used here. But these are some of the simulations that we've used that show this, and we are seeing what we haven't discussed too much is formation fluid displacement beyond the boundary of that simulation area as the CO2 is injected. Okay, and
thanks very much, Nick, for that question. We've got another question from Ash Palayalwa, who's with the Worley Parsons Group, and it's about the phase of the CO2. Does the absorption depend on the state of CO2? That is, if it's in supercritical phase or not, and how does that impact on absorption?
So I think if by absorption the questioner means the dissolution, then both supercritical CO2 and gaseous CO2 both are soluble in the formation fluid. Key controls on that, the degree of solubility, are things like temperature and also the salinity of the formation fluid. If it's a supercritical phase, and in most storage situations that's likely to be the case, except for perhaps in strongly depleted gas fields. If it's supercritical, then one of the primary controls on the amount of solution one can expect is the amount of contact that dense fluid has with the formation waters. So as we've shown, that dense phase, though still less dense than the surrounding waters, could migrate quite rapidly under gravity, and that's the amount of contact it has, the amount of mixing it has with the formation fluid will actually control the amount of solution. So there are different parameters. The more saline the formation is, the less soluble it is. So there are quite a few different parameters to consider. But these are things that we can easily measure in the reservoir before we start the injection process, and therefore we can feed those into our models to be able to predict that the amount of solution quite straightforwardly.
And we've just got following on from that question, we've just got a related question about modeling and solubility trapping from Rob Heath, who's with the Wandone CCS project in Queensland. And it's something that has come up, I think, repeatedly over the years relating to cell size. Rob's question is, what is the adequacy of the dynamic simulation model to model solubility trapping? he thinks that the amount of dissolved CO2 may be overestimated by the numerical models generated due to the assumption of instantaneous equilibrium of CO2 and water in each block. And I think following on from that, he says, does cell size matter?
We were having a discussion about that only last week, and certainly cell size is very important. And one of the again, one of the challenges in CCS is to create a series of different models and run a series of sensitivities that allow us to test the consequences of varying things like cell size. One of the big problems, of course, is that with lots of cells, the amount of calculations that any model is required to do goes up by orders of magnitude very exponentially, and it becomes impractical on even very powerful computers to be able to simulate adequately. So there are a number of ways to approach this, I think. Obviously, since doing sensitivity analyses will help simulating in a lot of detail small areas to generate the sort of amount of dissolution, the amount of trapping that might occur in small areas, carrying out maybe some supporting laboratory experiments as well, and then using the results of that to more carefully constrain the reservoir simulations, which are often done with fairly large cell sizes because of the to make the runs more achievable in realistic time frames. So yes, I think that's a very valid point, and it's certainly a big challenge. The cell size can overestimate the amount of solution that's predicted in a simple reservoir simulation, but what's required is to do different calculations at different scales to try and address that issue.
It sounds like this solubility trapping area of your talk has attracted a lot of interest from all over the world. I've got a question from Norway now, from Asa Slagstern, who's from the Research Council of Norway, and he was asking if you'd say something more about what type of experiments are required to improve the models with respect to prediction of time for solubility and mineralization trapping. And he's thinking in the sense, I guess it comes back to the scale question again, and taking another angle of in the lab or and at the pilot injection sites. So would you care to comment on the utility and application of models, of modeling and improvement of those modeling workflows at laboratory and pilot injection sites? What are the opportunities?
Yes, so there's, in terms of laboratory experiments, then there's been a lot of work done around the world, quite a bit done here in BGS actually, and that looks at two types of process. One is just simply reacting rocks and formation fluids with CO2, seeing how much dissolves into the formation water and how much of that might react with a given reservoir. And those experiments, what they do is they provide some of the rate information, the geochemical reaction rate information that is needed to constrain some of these model predictions. You can also undertake slightly more realistic simulations by pumping CO2-rich formation fluids through columns of rock in the laboratory. These can get up to several meters in length, so that's a slightly bigger scale. And they also simulate in a more realistic sense, the amount of reaction that can occur, the amount of residual trapping, and the amount of geochemical trapping that might occur. But we can also, as Asa has quite rightly pointed out, go to pilot scale tests. If you think about the Weyburn project as an example, an awful lot of data was acquired during that project that demonstrated quite rapid CO2 solution into the reservoir waters there, and the start of some reaction with the reservoir. That was a slightly different case, but essentially that is was able to demonstrate quite a bit of dissolution. So yes, we can look at both laboratory scale, very small scale, larger laboratory pilot scale tests, and even some demonstration projects. And it's perfectly possible, again, examples like Frio and Optway also have demonstrated that you can monitor the amount of CO2 being dissolved into the formation fluid and start to interact with the rock. So yes, all perfectly possible.
Thanks very much, Mike. We're just going up to a slightly higher level now in terms of some of the questions. One of the questions we have from Warren Moray Soares of Jacobs Engineering in the Netherlands is, what will happen when an earthquake occurs at the reservoir? I think he's talking about at this containment zone.
Well, I'll have a go at that one. I think, obviously, we won't be, if we can avoid it, putting CO2 storage anywhere near sort of active faults, certainly large active faults. So the first thing is to plan your storage as carefully as possible, and when you get down to the local level, to model, as we've been discussing, as Jonathan has shown, to model in pretty high detail the reservoir we're using, and so we know if there were faults, then we'd be able to avoid them. Essentially, that's the main answer to the question. We wouldn't want to be anywhere near an earthquake zone. And you may want to ask whether CO2 could cause an earthquake, and it's pretty unlikely that injection of these sorts of sizes could cause that kind of effect. We know that in shale gas, for example, in a related area, I suppose, there have been a few very small earthquakes recorded from fracking. But that's a very different kind of activity. So the answer to the question is we would avoid the possibility of an earthquake happening. But even in cases where injection is occurring, it's very unlikely that earthquakes would occur.
And I can just follow on from that. There is an example of an earthquake that occurred during a CO2 injection project in Nagaoka, pilot injection project in Japan. They had a magnitude 6 or 7. I can't remember exactly.
Yeah, I think it's about 6.8. Yeah,
6.8 magnitude earthquake at Nagaoka. In that sense, it was actually very close to the injection point. There was some local damage in terms of road damage and building damage, and I believe some of the surface infrastructure was very slightly damaged. But in terms of the injection system itself, in terms of the well that was being used to inject the CO2, that was not damaged. There's no evidence of CO2 leakage from that project during the time. And essentially, I think you have to visualize this as the whole rock mass all moving together. The only times that an earthquake would cause any potential leakage would be if you manage to displace either a fault cut through a well and cause leakage by breaking open the well, and I think you would be able to know that you were avoiding those areas, as Mike's already said, or even in an even more extreme case, actually breaching a catrock. And I think in both cases, your site characterization will ensure that you will be able to assess the vulnerability, if you like, of your storage site to those sorts of issues.
Thanks, Mike. I've got just time for one final question, I think. This one comes from Barry Nicholson, and I think it's quite a good one to wrap up on. It starts with more of a comment than a question, but he would like you to comment upon it. Barry says, the fact that there are a number of natural CO2 reservoirs which have been in place for millennia seems to indicate that solution trapping is limited, no matter what the time frame. Please comment.
Yeah, so that's a really good question. And there are, as and Barry's quite rightly said, there are many examples of essentially free CO2 at depth being trapped for hundreds of millions of years. and that's absolutely correct. And these are specific examples. They are probably examples where the CO2 has essentially displaced and dried out the reservoir in those cases. And it's perfectly correct that in certain small traps, perhaps similar to natural gas fields, then you will get very limited amounts of solution. And indeed, as a consequence of that, very limited amounts of mineral trapping as well. And indeed, even in other areas, if you don't have the right source of, or you don't have a source of calcium, for example, it's quite hard to get any large-scale calcite precipitation. So there will almost certainly be examples where the amount of solution is going to be limited. That's perfectly correct. And indeed, one thing that perhaps which is worth emphasising is that conceptual diagram of the relative proportions of each trapping mechanism is very much a concept, and for each specific site, the amount of dissolution will vary quite, could vary quite a lot between different sites, and again, it all depends on the things like the aquifer drive, the amount of contact, the amount of plume migration you get, the amount of mixing you get between the CO2 plume and the formation fluid. So yes, Barry's perfectly correct. These algal systems have been well documented in many cases. One example I can think of, 300 million years of free CO2 gas has been estimated. So yes, certainly CO2 can exist in a free state for very long periods of time. And again, that would be part of your assessment. That would be part of your simulation to try and assess, for your particular case, the degree of free CO2 that could be expected in the future. And you would have to make sure that your catwalk in those cases was very, very impermeable to free CO2 migration.
Thanks very much, Mike. And on that, just reflecting on the idiosyncratic nature of geology and the fact that the analogs are very useful, but the specific site investigation is absolutely vital. I think it's a good point to end on. While they say there's a sign of a good talk is lots of questions, and we've got a surfeit of those, we haven't been able to answer all or pose all those questions in the time that we've got. But we will continue the conversation with Mike and Jonathan and circulate their responses soon. So if you have any questions, please continue to submit them through to Angus Henderson in the email address provided in the invitation that you received. I'd like to thank everyone for their attendance, and a reminder that the webinar has been recorded and will be available on our website in the next few days, along with the slides used. I certainly hope that you found this website valuable, and once again, thanks to our presenters. Just by way of announcing, we're just a pre-announcement. Our next webinar will be scheduled on the 18th of this month. Jim Underschultz will be talking about CSIRO and Curtin's University work to assess storage basins for potential CO2 storage in Australia. The title of the talk is Basin Resource Management for Carbon Storage, an Australian Context. Thank you all for your time, and good evening or good morning as is appropriate for your time zone. Thanks again, and so long for now.